I'm Pete.
I'm Stephanie, and this is the Cool Part Show, our show all about innovative 3D printed parts.
This spacer grid has thin, precise walls at right angles. It looks like the most elaborate ice cube tray ever, and water does flow through it, and it does have a role in cooling.
But this spacer grid is actually intended for use inside of a pressurized water reactor.
Additive manufacturing for a critical component of a nuclear power plant on this episode of the Cool Parts Show. The Cool Parts Show is brought to you by Carpenter Additive. When it comes to managing metal powder, there is no one-size-fits-all approach. Stick around after the episode to learn more. Welcome to the Cool Parts Show.
If you like stories about interesting, unusual, unique 3D printed parts, you're in the right place. Make sure to subscribe to the channel, and you can also sign up for our all-access email to find out about new episodes a day early. Today in the show, we are looking at this part, which came to us still on its build plate. But the piece to pay attention to is this structure up top. This is a spacer grid. It would be used inside of a pressurized water reactor, a type of reactor that generates power using steam and water heated through nuclear fission. The square holes on the grid would be used to hold the fuel rods, the material that's actually driving the reaction, and then the round cylinders would be for the control rods, which would be made of a material to help speed up, slow down, or stop the reaction.
So, the spacer grid holds fuel rods, which contain material we associate with nuclear power, think uranium, but in a housing which has an outer coating that we'll refer to later. A fuel rod goes inside each of these square sections. If you look in closely, there are these dimple projections and within each section, and they hold each fuel rod precisely in place. There are a lot of these in a nuclear reactor. So there is an assembly that would have 14 of these spacer grids. There are hundreds of assemblies in any nuclear power plant. And these spacer grids wear out. This part has to be replaced every several years or so. So this is a relatively high volume production part for nuclear power, and also a part that is critical to the operation of nuclear power. The spacer grids in use today look very much like this. They're not exactly like this because today they're manufactured a more conventional way.
That's right. So 3D printing these spacer grids introduces assembly consolidation and also some new design possibilities, potentially. But before we get into that, let's talk more about how spacer grids are manufactured today. I want to introduce our first expert for this episode. This is Bill Cleary, lead engineer in the Digital and Innovation Group at Westinghouse Electric Company.
Westinghouse Electric is in the commercial nuclear business, and we provide cradle-to-grave services and products, including new reactors. Pressurized water reactors are one specific form of a light water reactor, and they work by nuclear fission reaction producing heat, and by flowing water through fuel assemblies that are being heated by that fission reaction, we create a warm water or hot water side that is then ran through a secondary heat exchanger, where that secondary side is then heated to boiling, and that produces steam, which turns the steam turbines, producing electricity. The requirement for the spacer grids there is that they maintain that fuel rod distance separating them from each other, which optimizes the neutronics of the fission reaction itself. And they also provide for good mixing of the coolant so that we can get as much of that heat that we want from those fuel rods, into the steam side of things. Current spacer grids are manufactured utilizing stampings, and stampings require very complex stamping dies. There are various forms of spacer grids that each require a different stamping die, and stamping dies are very expensive. The lead time for materials as well as for stamping dies easily can be in the 1 to 2 year time frame. So the current way of making spacer grids can be very challenging for the company.
Various pieces that are stamped are assembled together to make this grid, and they are joined together through a precise, painstaking welding process. Involves a lot of precision, a lot of skill, and there are some issues with this method of creating the spacer grid. There is lead time and cost built into that assembly and joining process, which is challenging. And also, this is an inflexible process. The design of this spacer grid is determined by the design of each of those stamped pieces that go into it, and that design is locked in place by the hard die tooling that is already created to make those forms. So, needless to say, additive manufacturing offers a very different option.
There's also the issue of the number of parts that you need in the conventional process. Bill told us that there are almost 40 pieces in a spacer grid that is made through that stamping and welding method. And so additive manufacturing is really attractive for several reasons, including assembly consolidation, part count reduction, reducing that manual labor, and it also could introduce some chances to more easily change and evolve the design of these grids.
So we identified spacer grids as an opportunity for AM in that they are a 38 piece component. They're also a very high volume component. There are approximately 14 spacer grids in one fuel assembly, and there are hundreds of fuel assemblies in a reactor, and those fuel assemblies are replaced every 5 years approximately. By being able to eliminate some of the yield losses and some of the challenges with manufacturing, by being able to print them is attractive. We looked at the time to produce new versions of spacer grids, and additive can address that concern very quickly with prototyping and then into production faster than having to build stamping dies to try new designs out, so to speak.
It's an attractive use case for additive. But from a distance, this isn't necessarily an attractive part for additive. We often associate additive manufacturing with geometric forms that are very organically complex and intricate. This is a complex form, but there is a lot of squareness here, a lot of right angles and orthogonality, and these thin, straight walls. We were actually really glad that we ended up getting this part still on the build plate, because that makes it clear this was successfully produced all in one piece, in one build, through additive manufacturing, through laser powder bed fusion. We haven't mentioned the material yet this is made out of. It is Inconel 718, nickel-based alloy. It was produced on an EOS M290 machine, and it was made by the team at Carnegie Mellon University.
So Westinghouse and Carnegie Mellon, they're both in Pennsylvania. They have a long history of working together to solve problems like this. And Westinghouse also has a subcontractor that has been making spacer grids the conventional way for them, that was interested in getting started with additive, that also got involved in this project. So those three organizations collaborated to develop and prove out the idea of 3D printing a spacer grid like this one. To talk more about the challenges that they were trying to solve, the problems that they wanted to overcome, I want to introduce somebody else to the story. This is Dr. Jack Booth. Jack is a professor of mechanical engineering at Carnegie Mellon University. He's also the co-director of their Next Manufacturing Center, which focuses on research and education in additive.
At the time that we started this project, we were not sure that we could build structures like this, particularly the tall, thin-walled structures. They could have some issues with deformations. The main constraints that Westinghouse put on us were dimensional constraints, and in fact we failed those dimensional constraints initially, and we worked out so we could satisfy them. There are small springs on the inside of these. There's a spring and there's a dimple, and the spring pushes against the fuel rod and holds it against the dimple. It ends up you have to have a consistent load versus displacement behavior for that spring, which means the geometry has to be consistent from spring to spring. And so that's an issue. The other one is a crush test. So in fact, these specimens were made for crush tests. And literally, there's a large weight which comes and hits these. and test how well they can survive an impact.
So let's talk about these thin walls. Each wall is 250 micron thick, a quarter of a millimeter thick. And the walls have to be very straight and very square with one another. Otherwise, the fuel rods would locate in the wrong place. And that requirement actually influenced the material choice. An easier nickel-based material to 3D print with potentially would have been a different alloy, Inconel 625, but using that metal would have entailed a heat treating step. And there was some concern that maybe the form and dimensions and straightness of these walls could shift a little in heat treat. Using Inconel 718 allowed for a process where 3D printing is not followed by heat treating. That enabled a process that achieves these thin, precise, straight walls. So the required quality, repeatability is there, and that fully solves maybe half of the challenge. Because the other half of the challenge is, can this part be made quickly enough, cheaply enough, that this process is cost competitive with production the way it's done now?
Yeah, so a lot of the work on this project actually was not in the design, but in the print parameters. They kind of started with the factory recommended settings on the machine and then found ways of tweaking those settings so that they could print this grid faster and still get the quality, still get the results that they wanted.
This was my student, Zia Udine, who came up with this. It ends up for these thin walls. The standard machine settings are that you fill in those walls with a little raster going back and forth, across the thickness, and it ends up that takes a lot more time and it's not necessary. So one of the big changes that he made was he changed the fill pattern for each of these walls so that you could build much faster. If you build faster, then your costs go down significantly. Another thing we found out is you can easily just double the layer thickness without sacrificing the geometric integrity of it. And immediately that doubles your speed, that halves your cost almost. And then the fill pattern issue saved us another 30%, a reduction of 30% in the build time.
So without changing this geometry, just changing the layer height and the way that the laser behaves, they were able to realize that 30% time savings. We should also mention that at the same time this work was happening at Carnegie Mellon, that subcontractor was also getting up and running with their own additive equipment, actually the same machine, the EOS M290. And so as part of this project, Jack's student Zia was able to work on both machines in both locations, help with the knowledge transfer there, and this project ended up demonstrating that it was possible to manufacture these spacer grids in both locations reliably.
So that set of 3D printing build parameters that the Carnegie Mellon team worked out that allowed this part to be produced effectively and cost effectively, but obviously 3D printing doesn't get you all the way there. Other operations are needed. Most obviously, this has to be separated from the build plate. That's done through a wire EDM step, electrical discharge machining, precision cutting to separate this piece from the plate. And then there was concern about the surface finish that's left by 3D printing. Potentially, likely, it is too rough. There was some concern related to that coating to the fuel rods. So an additional post-processing step was added to smooth out the walls.
Where the fuel rods contact the spacer grids, if that surface is too rough, then it could wear breaches in the cladding that contain the fissile material inside of the fuel rod, thus leaking that material into the coolant. Which creates a lot of expense and extended outage times. Part of the project actually looked at trying to reduce that surface roughness, which we were at least partially successful in. As it stands today, yet they're still a little bit too rough, and so we've been using electromechanical polishing to treat those surface areas that are in contact with the fuel rods. So in the future, looking to addressing the surface roughness, there are a number of pathways that we're looking at. Number one would be to improve the actual print roughness that's coming off the printer itself. Secondly, would be a more localized polishing process for those contact surfaces that are in contact with fuel rods. And thirdly, performing some studies that demonstrate that through additive, we can change the shape of the contact surfaces that do hold the fuel rods. And by doing that, the potential difference between the roughness and the wear surfaces can be adjusted such that we don't have any worse wear than what we have today with the current very smooth coil type surface.
So the process that Westinghouse and its manufacturer and Carnegie Mellon have worked out is a ready, capable, effective process for production, a new mode of production for these spacer grids. Next step, the team involved is finalizing how production will work, preparing what they've learned so far to adapt this into an ongoing production process for these spacer grids. And once they are made this way, that will bring significant change.
The spacer grid project opened a lot of people's eyes, as well as my own, to being able to adjust the process to build things that previously we thought were not going to be that readily buildable using additive manufacturing. The thin-walled structures that are required in a lot of our product, previously with the default parameter sets that are applied in these instances, they don't lend themselves very well to that type of structure. So by going through and really pushing the limits of the AM process, we were able to come up with a product that looks very promising. Through that, folks have said, well, if they can do it with spacer grids, they can probably do it with all these other components that have a lot more bulk to them and are much easier to prove out their properties with.
All right, let's recap.
All right. This part is a spacer grid. It would be used to hold the fuel and control rods inside of a pressurized water reactor. Currently, grids like this are made through a sheet metal fabrication process, but Carnegie Mellon and Westinghouse collaborated to develop this design instead, which is 3D printed from Inconel 718 through laser powder bed fusion, all in one piece.
Here's what's cool about it. This one piece replaces what used to be 38 separate pieces made through stamping, joined together through welding. The new process is more responsive, more flexible. Spacer grids made through additive manufacturing can be produced roughly as they are needed, and because there's not hard tooling in the form of a die to lock in the shape of each component, the design of the spacer grid can be allowed to evolve, adapt, and change as Westinghouse and its manufacturing partners see ways to make this better.
So the spacer grids are still a work in progress. Westinghouse is continuing to work on these with Carnegie Mellon, but this is not the only application for additive that Westinghouse has found. Bill told us about a couple of other components that are 3D printed that are being used in nuclear reactors right now. So if you want to see Bill talk about that, you can find the clip at thecoolpartshow.com/allaccess. Just sign in or sign up for free if you're not already a member.
And if additive manufacturing is empowering your production, we want to hear about it. What is your team learning about ways to produce a part that's important to your company through additive manufacturing? We might do an episode of the show about it. Email us, coolparts@additivemanufacturing.media.
Thanks for watching.
This episode's brought to you by Carpenter Additive. We're past the point of not knowing how to qualify metal 3D printed parts. We know, it's just that different end users of those parts have different qualification requirements. Additive manufacturing service providers have to navigate that, and Carpenter Additive has to think about that in tailoring powder management solutions.
Our customers typically will have, if they are a service provider, they will have a series of end user customers who may be, say, OEMs in the aerospace world. And each of them has a fairly large team of engineers who've been doing this for decades or more and have developed all these standards, regulations, paperwork. So It is certainly a challenge to thread the needle between all of these different requirements. We start really high level, we walk on the shop floor, we ask them about, okay, source to sink, how do you bring in the materials, goods in, send that material to each of the systems, and then what we're really interested in is how do they reuse that material. So what we do is called a value stream map. Pretty often that leads to a series of things that were either overlooked or hadn't really boiled up to the surface yet in terms of things that are potential risks or potential challenges or inefficiencies that exist. A lot of the customers we work with, especially in the more regulated industries such as space or medical or aerospace, have already been through those early learning stages. They've put 5+ years into this. They've done the product design and the design for additive manufacturing. And now they're starting to reach some of the more finicky problems that you get when you're at the scale of maybe 5-10 machines. You're running different materials simultaneously, you're doing different programs. Right, we get to take the best from the medical field and the aerospace field. We understand the specifications and the standards that exist in each of those fields, and we can sort of take the best elements of those and customize that to our customers.